All right, class, welcome to lecture 2. So today I want to begin, as I will every lecture, by reminding ourselves of what we just discussed, giving a brief recap of the previous lecture, and then I'll go on to start incorporating new material. We have a couple specific goals for today. The first is to re-examine some of the assertions we made in the previous lecture, some of the definitions I essentially ask you to take for granted, take without question. We will motivate a little more thoroughly and a little more rigorously, and we will discuss some of the implications for our kind of fundamental postulate of StatMech, which I'll review in a moment, for systems that are away from the idealization of a completely isolated system. Okay, but before we go there, let's remember where we've been. So we started the first lecture by making an observation that is so commonplace that you might not be as astounded as you really should be by the fact that you all know that the world is made out of atoms and molecules, and that therefore every material, everything in your vicinity, everything that you see is undergoing wild fluctuations on a scale that's just too small enough for you to notice. So we reminded ourselves that microscopically, fluctuations abound. And yet, macroscopically, on our scales, things look rather boring. We don't notice, we can't sense that chaos happening at the molecular scale. That's actually something we will think a little bit more carefully about this lecture. How do we reconcile the fact that on small scales things are happening continuously and yet we don't notice them? Why does the glass of water look boring? Why does it look like nothing's happening? When if I was able to look on the molecular level, water molecules would be continuously tumbling over one another. So something happens when we zoom out such that those fluctuations, those departures from average behavior, cease being so noticeable. Probably the most important lesson from the last lecture was the statement of our fundamental postulate. The statement which, though hard to prove, serves as the bedrock for everything that will happen in this class. A way to state this postulate is in words for an isolated system. One in which I wrap an insulation and thus fix the energy. I make rigid and thus fix the volume, and make impermeable, thus fixing the total number of particles. All microstates, which we denote little nu, are equally probable. Microstates being all of the gory details that specify the state of a system, all the positions and velocities of classical particles where I can specify both, or the total wave function of the system. Stated mathematically, probability, little p, of a microstate is equal to a constant we call 1 over omega, which depends on the energy, volume, and number of particles I've set, provided that microstate satisfies those constraints, that the energy is the energy I've set, the volume is the volume, and the number is the number. Otherwise, if it's not the right energy, not the right volume, or not the right number of particles, that probability is 0. Now that number, omega, then is just the total number of allowed microstates. So these are global constraints, which provided are satisfied. We have a very simple statistical statement about the likelihood of seeing some configuration. It's just a constant. In fact, that omega then has a probabilistic interpretation. It's just a normalization constant. If all outcomes are equally probable, the probability of seeing an individual outcome is just 1 over the total number. That total number then, if I sum up all the probability, gives me something that returns unit probability. If I have a head, if I flip a coin, there's 2 possible outcomes. I assume both are equally likely. That means the probability of flipping a coin and seeing a head is 1 over 2. All right. So after stating that fundamental postulate, we made some statistical deductions from it. Namely, that if all things are equally like all states are equally likely, the most likely outcome is that which maximizes omega, maximizes the number of ways something can happen. Often it behooves us to not mathematically extremize omega, but rather log of omega, a monotonic function whose maximum is in the same location as omegas. We thought about this in the context of this thought experiment of a beaker. Whereby we imagined a beaker setting a position where solute molecules could explore. Provided that beaker was massless, it could wander as it would. The probability of seeing it at a specific position, we labeled L, was just proportional to the number of ways it could be in state L, which we, in doing the counting, learned went like L to the n being the number of solutes. And we noted in passing that that was a very strong dependence on n. It was an exponential dependence on n. Finally, from that simple counting argument, we deduce something which is, I think, pretty spectacular. We actually deduced, just by doing that counting, the ideal gas law. Making an assertion that in an isolated system, all states are equally likely, we were able, in just a few lines, to note that the pressure of a gas was just proportional to its density. That was from basic statistical reasoning. The constant of proportionality was something we defined, we had to introduce. We called it beta. It was equal to how the number of states, or the log of the number of states, changes with energy, provided I'm in that isolated system, which means I was holding n and v fixed. Identifying that prefactor, or defining that prefactor as such, in order for the ideal gas law to take its normal form, we notice that we would have to equate that prefactor to 1 over a constant, so-called Boltzmann's constant, Kb, which is nothing but the ideal gas constant divided by Avogadro's number of particles. That beta then is just 1 over this fundamental constant times temperature. That was a definition. You should be very skeptical. Why is that definition reasonable? That's something I'll try to convince you of by the end of this lecture. All right. So let's begin with some new material. In fact, we will rehash some of the things we've already learned in a little bit more generality. In a discussion of probability, partitioning, and spontaneity. In macroscopic systems. Okay, so let's generalize a little bit away from our simple beaker and consider an isolated system. Here we draw a little box. As I said, an isolated system needs to not exchange energy with its surroundings. One way to physically have that happen is to wrap it in insulation. I'll use these little hatch marks as indicating that insulation. Yeah. Another way of saying an isolated system is a closed system. And now I'll draw an artificial partitioning positioned a distance L from the leftmost wall and separating instantaneously some amount of energy on the left, let's call it E1, from the right, let's call the energy at that instance on the right E2, and some set of mechanical variables, let's call it the vector x1, which is instantaneously x1 on the left and x2 on the right. So E and X in this isolated system are fixed. It's an isolated system, so the total energy can't change. So E, if I sum up the energy on the left and the energy on the right, E1 plus E2 is a constant variable. Energy is held fixed. X may be the total number of particles, may be the volume. Since this system is isolated or closed, the total number of particles can't change. Those walls are impermeable. The total volume can't change. The box is rigid. Which means that if I sum x1 and x2, the mechanical variables on the left, like the number of particles, with those on the right, that total x is similarly fixed. And this fictitious wall, this dashed line I've drawn here, at this instant, will denote it being at position L, and that is what partitions our two subsystems. All right, now we'll play a similar game to what we played before. Let's imagine that that partitioning can move at will, can move freely. If that wall can move, the probability then that I see it at some specific position L, we've argued before, is then just going to be proportional to the number of states at fixed L, at a given L. So P of L is the probability of seeing that wall at position L. Omega of L is the number of microstates consistent with that partitioning. Now, I've asserted this proportionality as I had last lecture. For those of you who that is not straightforward, I think it's worth a little brief aside. This can be shown in just 2 lines. The probability of L is equal to the sum over all the states conditioned on having that value of L times the probability of seeing that state. Now, if L is fixed, as is the energy and other mechanical variables, those probabilities are all the same for that given L position. The constant of proportionality then is the sum over all microstates without that condition. So sums over all possible values of L. That denominator is independent of L. It is equal to some total number of states called omega tot. Summing over all the states consistent with some L is what we called omega L. And so the probability of seeing the wall at position L is indeed proportional to the total number of ways the system can exist with fixed L. Again, if this is abstract, think about coins. If I was going to tell you, if I was going to ask for flipping 10 coins and seeing 5 heads and 5 tails, you intuitively know that that's a likely thing to have happen relative to the probability of seeing all heads. As we discussed last lecture, that is not because a specific sequence of that results in 5 heads and 5 tails is any more or less likely than having a sequence of all heads. A specific sequence is identical in probability to any other sequence. It's just 1/2 to however many coins I flip. But the number of ways that I can flip 10 coins and get 5 heads and 5 tails is much, much larger than the number of ways I could get all heads. There's only one way to get all heads. There are many, many ways to get 5 heads and 5 tails. So the probability of seeing 5 heads and 5 tails is much larger than the probability of seeing all heads, just because the number of ways that the former can happen is much larger. I'm saying nothing different here. If each state is equally likely, then the probability of seeing a given position of the wall is just proportional to the number of ways it could happen. Okay, that's a little bit of an aside. So we're going to ask the same question we did with the beaker. If this is true, if the wall can move, and this is an isolated system, we consider our postulate, where does the wall end up going? So let's call L star the most likely value. Let's imagine that the number of particles, the scale of this system is large. And let's assume, based off of our physical intuition, that for a large system, fluctuations are small. That is to say, when we take an Avogadro's number of particles, we don't notice fluctuations, we don't notice that liquid moving. So we'll assume that actually what we mean by equilibrium, a system unchanging macroscopically, is finding it at its average position. If fluctuations are small, once the system is at that most likely value, we aren't going to see deviations from it. So if I was to make a plot of log of omega, say versus L, let's imagine it has some form like so. That maximum, therefore, is L star. L star being the most likely value. The most likely value is the value that maximizes omega. And macroscopically, that's really what we mean by equilibrium. The state we are likely to find the system in, given it's left to its own devices, is its equilibrium state. It's not changing. If macroscopically fluctuations are small, if the system is not changing, it is therefore at equilibrium. All right, so now let's see what happens if we imagine moving the system away from this most likely value. So this maximum, if fluctuations are small, is overwhelmingly likely. Let's imagine making a virtual displacement, taking L to L star plus some delta L. So let's call that L star plus delta L. Let's imagine moving the system in some thought experiment to that new location. I say it's virtual because I'm imagining I can do this with the same energy and fixed other mechanical variables. All right, it's manifestly the case, therefore, if we moved away from the maximum, it must be that the log of omega evaluated at the fixed energy, the fixed mechanical variables, and L star plus delta L must be less than the number of states at fixed energy, mechanical variables, and L star. If L star denotes the location of the maximum, if I move away from that maximum, omega must decrease. There are fewer states away from the most probable location of L. Another way to say this is that the number of states at fixed energy and mechanical variables, now this is total energy, total number of mechanical variables with different partitionings. If I constrain the system to be in some state, that number of states is less than or equal to the number of states the system has if I do not apply a constraint. If I let the system evolve as it will, the most likely value is what I'll see. That's the value that maximizes the number of states for this isolated system. So if I enforce a displacement from that most likely position, it must be the case that the number of states decrease. More generally, we would say that log of omega must decrease with a displacement from equilibrium. If macroscopically, what I mean by equilibrium is the state of the system left unconstrained, that if I take that system and I move it from equilibrium, the number of states that the system can sample that are available to the system is smaller. An equivocal or equivalent thought experiment let's imagine beginning with the system at L plus delta L. L star plus delta L with the same fixed total energy and other mechanical variables. What do we expect to happen? If we plot log of omega versus L, here's L star. That's the functional form of log of omega. Poorly drawn. Let me try that again. There we go. Maximum's in the right place. Here's L star plus delta L. So we start here. What's going to happen? Well, that's a very improbable state to have found the system in. More likely than not, if I walk away and come back, look at the state again, make another measurement on the system, more likely than not, we will find the wall has moved to a state of higher probability. Back to that maximum value at L star. Now, note, I should be careful and note a subtlety. I'm not saying dynamically what will happen. I'm saying that if I look at the system at one instance and I see a very rare possibility, very rare outcome, if I then look at the system again, with overwhelmingly high probability, it's more likely to be seen or observed at a position of much higher probability. If your friend flips 10 coins and gets all heads, if you flip another 10 coins with very high probability, you won't get 10 heads again. You'll have nearly 50-50 heads and tails. So starting from a very improbable state, it is with high probability likely to see the system move to a high probable state. But the reverse is not true. If I started in the high probable state, it's very, very, very unlikely to see the wall move to a very improbable state. For large n, for a large system, we would say that L star plus delta L moves to L star spontaneously with high probability. A low probability state spontaneously moves to a high probability state, but L star does not go to L star plus delta R. In a very large system, it does not happen, or at least happens really, really improbably. A way to summarize what we've just deduced, again, just pure statistical reasoning, we would say for any spontaneous process at equilibrium, in our isolated system, so fixing the total energy and all the mechanical variables, we expect that the log of the number of states to increase. With overwhelming probability, an improbable state becomes a probable state. This is a statement of probability, but it's a statement of a spontaneous process. The wall will spontaneously move from a position of low probability to high probability. What does that start to sound like? There are little demons probably sitting on your shoulder, tugging at your ear, reminding you of a concept you learned long ago. What is that? A Mr. Ludwig Boltzmann first did this little bit of statistical reasoning and wrote down an equation, now sits on his tombstone, that identified this quantity which spontaneously increases, log of omega, with a thermodynamic quantity that had been known since Carnot, called the entropy. In fact, Boltzmann said that they were equivalent up to a constant, Kb, which we now call Boltzmann's constant. So pure spontaneous, or pure statistical reasoning, improbable becomes probable, is nothing but the second law in disguise. Or rather, the second law is nothing but a statement of probability. Why that constant? Well, that constant, because those silly people building engines gave entropy units. So entropy has units. Omega does not. Omega is just a number, it's just a number of states. So there needed to be a constant proportionality to make that equivalence. Why the log? Well, that's something we'll explore right now. So we should ask, again, this is a definition for what is meant by entropy in a microscopic system. We should ask, does it act like an entropy? Let's go back to a specific case where we can work things out concretely. Let's consider a dilute solution. So here's our box. We have solute particles filling that box. There they are. For concreteness, let's put our solvent in there. All right. Now let's grid up this system. Put in some fictitious boundaries that partition the system into cells. Now, unlike when we did the counting for the ideal gas law, let's imagine that these cells are large. Let's give it the same little v to denote its volume, but imagine that it's big enough such that one cell is statistically independent of the others. That is, that the range of interactions is small, such that the state of that cell, being so large, its volume vastly overtakes its surface area, such that, to a very good approximation, its molecular state is independent of the cells that neighbor it. M will denote the total number of cells, computable by asking for the total volume of the total system, capital V, dividing by the volume of each cell. Let rho be the total number of solutes in the total volume. And if rho is N over V and M is big V over little v, another way to write M is the number of particles divided by rho times little v. That's the number of cells. So there are M independent cells, independent subsystems. How many microstates are there? Well, let's let omega denote the total number of states. Let's imagine that little omega tilde is the number of microstates in one cell. That's just a definition. If we knew lots of details about that cell, what the solutes were, what the solvent is, we could count that number of states. Now, each one of those cells is constructed such that they're all statistically equivalent and they're independent, which means that the number of states in the M independent subvolumes is then just the number of states in one of the subsystems to the m, the number of independent subsystems we have. I can rewrite that, noting a way of rewriting m as n over rho times little v. By the property of exponentials, that is equivalent to saying omega to the rho times little v, all raised to capital N. Since m is n times rho over v. The bracketed quantity I can denote as omega, and what I've just uncovered is that the total number of states, if I have m independent subvolumes, goes as some constant to the n, goes exponentially in the number of particles. What should little omega depend on? Well, it should depend on the extent, the volume of that cell. By definition, it depends on rho. Now, it's a subsystem. It does not know about the total energy of the system, but rather the energy density. Let's call that epsilon. These are all intensive quantities. They don't change as I add more independent subsystems. Another way to say that is it doesn't change, little omega we don't expect to change if I add more cells to the system. So we could rewrite this as capital omega, the total number of states, as little omega, which depends on things like the energy density, to the n. This specific relationship of the exponential dependence of the scale of the system on a quantity like the total number of microstates going exponentially with the scale of the system has a known mathematical form. It's known as a large deviation form. And such relationships are ubiquitous in thermodynamics and statistical mechanics. And we so much so that we generically expect an exponential dependence on n, even outside of this dilute solution. In fact, all we've really needed to assume is that we can carve up the system into statistically independent units. So that just is a statement of the scales over which systems will interact. As long as those are finite, we can carve up the system into subvolumes. We should expect this large deviation form to arise. Okay, so we have a form for omega. What are the consequences for Boltzmann's definition of the entropy? Well, if S from Boltzmann is a number that gives it units, the log of the number of states, given this large deviation form, we plug in omega to the n. Property of logarithm says that we can pull that n outside, and we have kb n log omega. So by virtue of the relationship between the entropy and the number of states entering through a logarithm, and the generic property that the number of states goes exponentially in the system size, we find as a consequence that the entropy is an extensive quantity. So in that, it acts like an entropy. It is an extensive quantity, and it tells us about the direction of spontaneous change. All right. Well, let's keep going. We have worked within this fundamental postulate, which applies in a pretty restrictive setting, a setting of a completely isolated system. Most systems are not isolated. Spoiler alert. Can we use this postulate to say something about those cases? Let's imagine constructing a system that can exchange energy in a very specific sort of way. Let's say that we imagine some system which can exchange energy with what we'll call a bath, which is nothing but a very large surroundings. So this would be in a case of an open system. Let's construct this composite system plus bath in a specific way. Let's take our initially isolated system, wrapped in insulation, rigid and impermeable, which we know how to describe. This isolated system is something whose states are equally likely. And within that system, pull out a piece that we care about. And let's imagine that that piece is itself impermeable, and that it will fix the number of particles. It's rigid, it will fix the volume, but it's not insulated. So it can exchange energy. That rest of the surroundings we'll call the bath. So the total energy in this composite system plus bath is equal to the energy of the system, which depends on some microstate, is computable if we know the microstate it's in, plus the energy of the bath, which itself is computable by knowing its microstate. So the total energy, everything inside this region of this insulation, is fixed. So the composite system plus bath, we know how to describe. Its states are equally likely, but what we want to be able to say is something about the system specifically. If we were to find the system in some microstate nu, It is possible that for a given microstate of the system, the bath could adopt any number of microstates. The only requirement is that those bath microstates satisfy the constraint that the total energy is fixed. So if EB is the energy of the bath in some state nu B, it must be the case that that state satisfies conservation of total energy given the state of the system. Now, all of those bath states, if they have this constant energy, have equal probability of occurring. Now let's assume the bath is really big. And let's ask about how many states we should expect to find to hold this constraint, to follow this constraint of fixing the total energy. That's a relevant question because it is going to tell us the probability of seeing the state in some specific microstate, the system in some specific microstate. Specifically, if I was going to ask about the probability of seeing the system in some specific state, well, because there are many possible bath states available to it, the total probability of seeing the specific system state is the accumulated probability of that specific system state in any possible bath state the world can be in, because this specifies the total microstate. Now, each combined microstate is equally probable. It has a probability of 1 over the total number of states at this fixed total energy. But there are many possible bath states commensurate with the system being in some specific state. So let's denote the number of those bath states, omega b. Its energy simply needs to be the energy required to conserve total energy. So the probability of seeing a specific system state is just proportional to the number of ways that system state can happen, which, given you fix the system in some state, is just the number of corresponding bath states available to it. So it is proportional to the number of bath states with energy EB, such that the bath state nu B, if I plug it into its energy, returns the total energy less than the energy of the system. Now, we've assumed that this bath is really big. If the bath is really big and energies are extensive, that means that the total energy is dominated by the energy of the bath, or rather that the energy of the system relative to the total energy is small. If it's small, while we don't know the specific form of omega b, we can infer some of its properties by imagining we can Taylor expand it about this fixed total energy. Right. So how do we do that? So again, we don't know the form of omega b, but let's approximate it. And let's not approximate it directly, but the log of it. So omega b evaluated at its energy, assuming that the energy of the system is small, is to first order, just log omega b at the total energy. And the first order correction is going to be how the number of bath states change with energy times the energy of that system. Again, just a quick reminder on Taylor series, that's like saying I have some function f that I want to evaluate at x plus a. If a is small, that means I can, at first order, 0th order, approximate it as the value of that function f at a0. And to first order, I have a correction proportional to a times how f changes with x, evaluated in the absence of that a. Now, we have seen this quantity before, how the number of states change with energy. That's what we called beta. Now, this is how the number of bath states change with energy. So let's, for the time being, call it beta b. It is a property of the bath. Now, putting together, we have the log of the probability of some system states is proportional to, when I take the log, that constant proportionality becomes a constant shift value. So it's equal to some constant minus beta b times the energy of that state. Taking the exponential, the probability of the microstate is then proportional to e to the minus beta b, the energy of that state. Whoop. So in an open system, oh, that's terrible. Let's try that one more time. So in an open system, a system which can exchange energy, just using our fundamental postulate and some algebra, we arrive at a statement of the probability of states, which is now exponential. It depends on the energy of that state. All states are not equally likely. They rather are exponentially less likely if they have higher energy. This is known as Boltzmann's distribution. So being able to exchange energy results in an apparent bias for seeing microstates of the system that depends on the system's energy. So in an open system, a system that can exchange energy with its surroundings, all states are no longer equally likely. Some are actually favored. I often find this much more intuitive. Lower energy states, I think we have intuition, mechanical intuition, seem more likely to occur, but that's only in systems that can actually exchange energy. If the total energy is fixed, all states are equally likely. You can't find a state with a different energy, so one state is just as probable as another. Now, it's worth reminding ourselves of how we got there. We started with our fundamental postulate, and we deduced this exponential bias by attaching our system to a large bath. And we're free to choose that bath to be as big as we want, such that this Taylor series, which gave us this approximate form, can be as sharp as we want it to be. In fact, you will explore in your homework how rapidly converging this series is. For omegas, which typically scale exponentially, and the scale is in the size of the system, and energies which are also extensive, this Taylor series converges exponentially rapidly. All right, so now we can actually talk about the likelihood of seeing different energies in our system. So let's ask a basic question. What is the probability of now seeing a specific energy? How is energy distributed in a system that can exchange energy with its surroundings? Well, the Boltzmann distribution tells us that there's an exponential preference to lower energy, provided that beta B is positive, which it is. But it's not as simple as that, because there are many potential states with the same energy. Let's call that energy E. And all of them have the same probability. So P of E is equal to a sum over all states with energy E the probability of seeing a value of the energy is just the probability of all states summed up with that energy. All of those states have, in a system that can exchange energy, this Boltzmann factor. But in addition, there's many of them, and we've actually already encountered a name for that total number. The total number of states with fixed energy is what we've called omega. So the probability of seeing some energy is a product of the number of ways that energy can occur, the number of states with that energy, now times this exponential factor. Let's equate this, or let's rewrite it in the following way. If we bring that omega, remember we were able to argue that omega, capital Omega, has a large deviation form. It went like little omega to the n. If we took exponential of log of omega, that's equal to omega. That's a very fancy way to rewrite omega. Let's just put it up in an exponential. We could factor out n. We get beta b times epsilon being the energy per particle, minus log omega, where again, epsilon is E per n. So again, the probability of seeing some energy also has a large deviation form. It's exponential in the scale of the system. Beta, epsilon, and log omega are all intensive quantities. The scale is taken out of them. All of the scale of the system enters in exponentially. All right, let's understand the consequences of that large deviation scaling for energy. Let phi of epsilon equal beta b times epsilon minus log omega, the argument of that exponential with the n factored out. If we were to plot phi as a function of epsilon, well, we have a piece that goes linearly with epsilon. That's beta b times epsilon. As long as beta b is constant, phi will increase linearly with it. Omega is itself a function of epsilon, as long as it itself is not an exponential function of epsilon. Its functional form will look something like this. That's minus a log. So if I sum the two, the line beta times epsilon and the minus log function, I will get something that looks something like this. At small values of epsilon, log omega varies more rapidly than the line, but at large values of epsilon, the line overtakes it, so it's non-monotonic. It has a minimum. Let's denote that minimum as epsilon star. Let's move this down just a bit. Okay, the probability of the energy we said had this large deviation form. That phi is in the argument of the exponential. So let's see what happens when we plot e to the minus phi. Because that's how the probability distribution of the energy varies with it. So minus flips this parabola upside down. Exponential makes it much more sharp. So if I put epsilon star, the location of its minima, on the plot, we should expect that e to the minus epsilon looks something like this. So the probability of some energy is proportional to e to the minus phi, which means that that value of epsilon is the most probable value. Now, the large deviation form tells us that P of energy, the probability of observing some energy, as I increase the scale of the system, takes this function here, e to the minus phi, and raises it to the n. So e to the minus n now times phi. If e to the phi has a peak at epsilon, e to the minus n times phi, if n is big, the only value that you'll see is epsilon star, that most probable value. in this little sleight of hand, in this little simple algebraic deduction, we've just uncovered the apparent paradox that we started the class with. We acknowledge atoms and molecules exist and that they undergo complex chaotic dynamics, but we don't see it on large scales. We don't notice fluctuations. The fact that probabilities, for example, the probability of the energy, an extensive quantity, has a large deviation form means that if n is big, the distribution is incredibly sharply peaked at its most probable value. Macroscopically, if n is Avogadro's number, only one value of the energy is ever observed. I like to think of this as being the explanation for why things look so boring at the macroscopic scale. We, with exponentially small likelihood, never see fluctuations away from the mean. All right. There's one last thing to do in this lecture, and that is to reconsider with some scrutiny a definition we've introduced. Boltzmann told us that the entropy was a constant times the log of omega. We have defined beta as how the log of omega changes with the energy. Substituting log of omega, we find that 1 over kb is how the entropy changes with energy, or that inverse temperature is equal to how the entropy changes with energy. You can drop the subscripts, it's true for all subscripts. This is actually the thermodynamic definition of temperature. This is what those guys building heat engines, how they defined temperature originally, was a measure of how the entropy changed with energy. So that's kind of interesting. It is a consistency check. It says that our definitions are self-consistent with what was previously known. That's really not very sufficient. That's really not very convincing. We should ask, does this definition actually correspond with our physical reality? Does this definition actually give you behavior that acts like a temperature acts? So does this definition make sense? Let's explore this by asking a question. What's the maximum value of P of E, or P of epsilon? What's the most likely value of the energy? What's the most likely state of the energy in the system? The most likely value the maximum in the probability P of epsilon is going to be the minimum of this function phi of epsilon, because n is a strictly positive number, which we can deduce by taking the derivative of phi of epsilon with respect to epsilon, evaluating it at this epsilon star, which we denoted as its most probable value, and setting that differential equal to 0. Okay, that requires some reminders of our definitions. We defined phi of epsilon as beta b epsilon minus log omega of epsilon. We want to take that derivative and set it equal to 0. The first is simple. That just returns beta b. That is then going to be equal to the derivative of log of omega with respect to epsilon. Notice that beta b, the beta of the bath, is equal to properties just of the system, the number of states in the system at fixed energy. Now, epsilon is the total energy divided by the scale of the system. So I could resubstitute in the total energy, costing me a factor of n. In log omega, if omega, little omega has that large deviation form, that's the same as capital omega. So the most likely value of the energy of the system is given by how the number of microstates in the system changes with energy, and that being equal to how the number of states of the bath change with energy. Both of those are these beta functions. So what we've just deduced is at equilibrium in a macroscopic system, the most probable value corresponds to the case where the temperature of the bath is equal to the temperature of the system. Well, we already knew that. That's our expectation from equilibrium. Stated in words, at equilibrium, the most probable state is given by beta b equals beta cis. The temperatures are equivalent, so we no longer need to worry about subscripts. We can just define it as beta. A system in contact with the bath will come to its same temperature. Or TB equals T cis equals T. So then, to me, that seems like a very sensible definition for the temperature. It is something which corresponds with our everyday reality. It's a definition consistent with the fact that if I place a system at one temperature in contact with the surroundings at another temperature, equilibrium, the direction of spontaneous change, the position where the system stops changing, is given by an equivalence of temperatures, where equilibrium is that state where the temperature of that system is equal to the temperature of that bath. So it checks out. All right, that's all I got. Stay tuned for lecture 3, coming to you Wednesday night.